Okay, we make use of the result that we obtained for the scaleless time that was tau, and tau was omega 0 t. Okay, there is no big difference at all, just substitution, change of variable. So if you learn mathematics, you are able to find a logical structure, but at the end of the day, or at the beginning of your equation, you you need to separate out all of the physical variables, physical scales, to make the equation to be solvable in an easy way with the dimensionless parameter as mathematicians do. Okay, so previously we have obtained the equation that was taken by the derivatives of the scaleless variable tau. However, in physics, there is always a scale, time, and inverse time. We turn on the physical scale. That is the topic of this part 2. Okay, omega 0 square root k over m, double derivative, so omega 0 squared k over m, and actually it originates from omega 0 squared dt squared in the denominator. So this guy appears as m over k. You could have divided this equation with k, so m over k, double time derivative, x equals 0. Okay, what you have is this kind of form. So this one was identified with d squared, d tau squared in our previous calculation. And this is sum of this operator plus 1 exists. That means this operator is dimensionless. So you could have checked this with this. Using that fact, we can revive the scale out of the equation. Our previous solution was expressed in terms of scaleless variable tau, but now it should be this physical scale should be turned on, and after that this actual physical function appears. As you know, you cannot substitute t directly to the cosine because cosine has terms of various powers, and time has a certain physical dimensions, so it is impossible to be substituted directly to cosine. However, this is dimensionless quantity, so you can substitute it without problem. Find that the general solution is this. We know already the solution can be obtained. In the previous class, we have made use of cosine tau and sine tau. You can follow the same way to evaluate the double integral. However, the integral and the derivative for the exponential function is much simpler than cosine and sine. That flips the sign depending on the number of application of the integral or derivative. So this multiplication or division of the exponential, the I factor, imaginary number, pure imaginary number I factor, they are consistent always. As a result, we carry out the same calculation. I think I don't have to explain the detail of this step-by-step computation. Finally, we will find the same structure as we have done with the cosine and sine. Finally, we have found the linear combination of these two functions is the general solution because these C1 and C2 completely determines the initial value of the position and initial value of the velocity. So you can make use of either way. Use the exponential e to the I theta is cosine theta plus I sine theta, Euler's formula, or just a direct substitution of cosine and sine. It depends on your situation. You know, you can combine any sinusoidal functions, C1 cosine theta, C2 sine theta, then you can pull out the square root of C1 plus C2 squared, and the C1 squared plus C2 squared cosine theta sine theta, C2 square root C1 squared plus C2 squared, and then put it as a cosine delta and cosine sine delta, because the square C1 squared plus the C2 squared divided by C1 squared plus C2 squared, it is always 1. So we can always parameterize these two as a cosine and sine, or sine and cosine. In case you have chosen cosine and sine, then your answer will be C1 squared to C2 squared plus cosine theta minus delta. Or if you use this, your answer will be sine theta plus delta. Either way, you have amplitude and sine or cosine omega 0 t minus delta plus delta. These are two parameters, or C1, C2, these two parameters, or e to the I theta, e to the minus I theta, this style, this parameterization. Either way, these two are the basis functions of a linear equation, linear differential equation. And these two are the basis function. These two are the basis function for your differential equation. Whatever. You can always choose any different way, but it is just like the change of basis in the Euclidean space. Okay, we say that the solution of this differential equation constructs a very similar space, just like a vector space. It is called the Hilbert space.